Now, this is our second type of bonding. Our first kind of bonding was metallic. And our second kind of bonding is ionic bonding. And most of our metals on our periodic table are not found as pure metals in nature. Definitely our group 1 metals and our group 2 metals. In fact, there are very few metals that are found in nature as just a pure metal. Gold, silver, copper can be found as the native metal. Which means that by and large, most of our metals have undergone a chemical reaction with something. And they're no longer just a metal. And they do this to achieve stability. Chemical reactions involve something going from a higher energy state to a lower energy state, by and large. And so we know that sodium, or our group 1 metals, are highly reactive, and we have to keep them under oil to try and prevent them from reacting with the oxygen in the atmosphere or water. And some of our other metals are also quite reactive, and they will also form compounds with non-metals generally to achieve this stability. When our metals react to form a compound, the compound they form are called ionic compounds. So here, well, by and large, they are metal cations. What we have in none of my whiteboard markers are working. It must be the end of the term. They're all tired like me. Ionic compounds contain cations and anions. The cation has a positive charge, and the anion has a negative charge. And it is this difference in charge that causes them to attract opposite. And it allows them to build up a structure based on attracting more of the relevant charged particles into a spot. So if there's a gap where it's mainly negative charges around, then a positively charged ion can slot into that spot, and it will then neutralize, if you like, that charge. Now, if we look at how we form our ions, if we think about our sodium metal and how we've got one valence electron, and I won't worry about going into any more detail what's inside, because all of the chemistry, all chemical reactions only involve valence electrons. Nothing inside is involved in the chemical reaction. So if I have, this is then a sodium atom, and if I have a chlorine atom, what's the valency of a chlorine atom? 1. Because valency is how many bonds you can form, not how many valence electrons you have. Now, we know that the sodium is very reactive. We have to store it under oil in order to prevent it from reacting. And the chlorine atom is also very reactive. And if we brought these together, then the sodium completely 100% donates its valence electron to the chlorine. Okay, so we have donating electron. But this part here is a chemical reaction. know it's a chemical reaction because we've had this movement of electrons from one substance to another. And what we end up with then is the sodium ion. And because it's lost its valence electron, the sodium ion is much smaller than the sodium atom. It's able to draw in its remaining electrons closer because there's a charge differential now between the electrons and the nucleus. The chloride ion ends up larger because it was able to hold its 7 valence electrons this close prior to the reaction, but now it's got more electrons than it has protons, and so they are held further apart. But they are both stable. They're both stable. This is the sodium ion and the chloride ion. Because they have achieved noble gas stability. And by that we mean a full outer shell. Now you might also notice that the chlorine's name's changed. So if we're talking about chlorine, we're talking about the atom. And if we're talking about chloride, then we're talking about the ion. And on your table of common ions, you'll see that our negatively charged ions are all going to end in "ide", like fluoride, iodide, bromide, oxide, hydride. They all end in "ide" as the negatively charged ion. Our positively charged ion's name doesn't change. Okay, so we started out with sodium, and it's still called sodium. The only difference here is that this one's the atom and this one is the ion. Okay, so here we have formed some ions, and these two are attracted to each other. It's just an irresistible force for the two of them, and so they are going to stay bonded together. But what happens is, if there are more of these ions around, they are going to build on to this structure so that another sodium ion can end up arranged around the negatively charged chloride ion. And then the chloride ions are going to build up around the sodium ions. And they just build in to any of the available spaces where that charged particle can fit, knowing that like charges repel and opposite charges attract. And what we build up is an ionic crystal lattice. Formed by these alternating charged particles fitting together. Okay, so these ones here before the reaction, these are not ions, they're atoms. But once we have our charged particles, these are now ions, where our positively charged ions are called cations and our negatively charged ions are called anions. And they come together in an organised crystal lattice. in a way that keeps the like charges apart and the opposite charges close together. And the attraction is an electrostatic. Force of attraction between those oppositely charged ions that keeps the solid together. Now, all of our ionic compounds are solids under standard conditions. And in fact, for a lot of them, we have to add a lot of energy to melt them. What does that tell you about the strength of the ionic bond? It's a strong bond. If I have to add a lot of energy to melt something to make it go from a solid to a liquid, then that means that these electrostatic forces of attraction between the ions are strong. Has anyone got any question at the moment? Anything? Now, if I did melt this sodium chloride, and I said I needed a lot of energy to do it. If I put some electrodes in here, will it conduct electricity?
Yes. I don't know.
You don't know, but
50% chance.
50% chance, yeah, yes or no, okay. Let's hope we can get better odds than 50%. If it's yes, why? If it's no, why?
Has that reaction already taken place?
It's already taken place, and now we had some salt and we melted it.
Because everything's now balanced, does that mean that it can't conduct electricity? Because we've got an even amount of plus and minus, because we sort of spoke about the fact of the negative charge being the thing that could carry the electrical current through. So if we've now got an even amount of both, does that mean that it doesn't?
Well, that's a good thought.
Okay, I'm changing my answer. So in the metallic bonding, it's a good conductor because it has the valence electron that moves freely to conduct the electricity. Whereas here we don't have any valence electrons because the sodium has given one away to the chlorine, and they both
Have net full
don't
shells.
have.
Okay. Any other thoughts?
I think I agree with them, but I'm still, and just another point to add, chlorine is still a negatively charged ion now, so I
So you're thinking?
wonder if that has any impact on whether it can conduct any electricity, because it is negatively charged and would have one extra electron, although it is still bonded to the...
Yeah.
Maybe just building on what Riel said, now that I think about it a bit more, is it just simply because because they still have valence electrons, like the ions still have valence electrons, but they're not delocalized, so they can't carry that current along, maybe.
Okay. Any other thoughts? No, this is good. This is good because it gets the old brain cells moving. Okay, so the answer is yes, this can conduct electricity. No. And the reason is that what we need for electricity is charged particles to move. And because these are molten, they can move. And yeah, the chloride ion, so just say this is a positive end, this is the negative end. Well, the chloride ions are going to be attracted to the positive end, but the sodium ions will be attracted to the negative end as well. So what we end up with is being able to conduct electricity because all of the charged particles will move. But I like all that thinking. Okay, so the chloride ions heading over to the positive end.
Does this does this work for all ionically bonded things?
So remember I said I melted it. So this is as a liquid. 100% of ionic compounds in the liquid state conduct electricity. Now if we think about this as being a solid, okay, so this is a solid and we said it actually requires a lot of energy to melt ionic compounds. Do you think this one can conduct electricity? Can it conduct as a solid? What did I say we need to be able to happen over here?
Charged particles.
Are able to move. And in this case of our ionic compound, this is the cations and anions. So, what about our solid then? No, because
If the carbon it's already been stated that the bonds between strong, so they wouldn't be able to move at all.
okay, yeah. So we have strong bonds, but the ions are fixed. And therefore they cannot conduct. Okay, good-o. I'm just going to think about another option. I don't know if you're going to see the screen. I have to recharge my whiteboard markers. Just say, because this is sodium chloride, which is like salt, and that dissolves readily in water, doesn't it? So just say instead of melting the sodium chloride, I dissolved the sodium chloride in water. So that means I've got some water molecules in here as well. Is that one going to be able to conduct electricity? How about you have a minute to discuss at your tables?
And that's why you don't chug a toast.
Could be the same.
Okay, what do we think? Who's voting for yes, it will conduct?
A.
Who's voting for no, it won't? This is great. I love these sorts of things. Yes, it will conduct because they can still move. Okay, but it's better to commit to something and it be wrong than to sort of be wishy-washy about it because it doesn't stick in your brain as much. So it can conduct in liquid or aqueous. Okay, so liquid means it's melted. It's molten if it's liquid. Aqueous means in water. we've used this symbol before where, you know, we have our liquid, solid, gas, and aqueous. Okay, when we're writing out a chemical equation, we need to remember that these are our states. So aqueous means in water. Okay, so yeah, we can conduct as a liquid or in a molten state, but we can't conduct as a solid because, yes, those ions are fixed, yes, Amy?
Can the water particles conduct as well, or because they've got like a covalent bond, so they're sharing? So like